Thank you for joining my presentation on MPI-BugBench, which is our framework for assessing MPI correctness checking tools. So we have a problem with the MPI API in the sense that it can be considered quite error-prone. For example, we need to manually specify the data type for a send operation, and if you specify the wrong data type, then you can have some errors there. But apart from these error proneness of the MPI API, also correctness checking tool support is desired due to the inherent complexity of programming applications with many different processes. Basically, the more and more processes you have, the more and more complicated things get. And then correctness checking tool support comes in handy as it can point out the errors that you've made so that you can then fix the errors and hopefully get to a correct application in the end. One problem that we encounter here are that correctness checking tools are hard to compare, especially their real-world applicability is often not sufficiently evaluated, because the way how tool evaluation is done most of the time is that if you develop a new correctness checking tools, you have a specific use case in mind, specific set of MPI operation, for example, that you're targeting, and then you will write some test cases in order to test if your tool works good for these kind of MPI operations that you have in mind. But then the question that remains open is, okay, what's with other MPI operations? Can your tool also handle other MPI operations, and how does it compare to other tools in these kind of operations? And especially also we want to test for the real-world applicability of such MPI correctness tools. Therefore, we invented the MPI correctness benchmark suite, MPI-BugBench, which is a collaborative effort. So basically, there were some previous work on that around where we have different correctness benchmarks, one developed by us at the Technical University in Darmstadt, and another one developed by INRIA in France, that basically arise at the same time. And then also there is the RMA race bench developed in Aachen. And for MPI-BugBench, we want to unify all of those into one unified MPI correctness benchmark so that you can then use only MPI-BugBench, and it has all of the different test cases from all of those correctness benchmarks combined. And I will also explain how we then further evolve the test case generation in MPI-BugBench to make this test for the real-world applicability of the MPI tools. So in MPI, you can make several different errors. An example would be some errors that you can make inside of a single call. You see an example of on the slide where we want to send a message with negative message length. I don't know how this should work, so you can have some invalid parameters there. Additionally, there can be some errors that are local to one process. An example would be here, violation of a request lifecycle. So we have an ISEND operation, and then we don't wait for completion on the ISEND operation and immediately reuse the request object to also perform the IReceive operations here on the same request object. And then we have no way to check for completion of this ISEND operation anymore. So it's also invalid if we override the active request for the ISEND operation before checking for completion. And of course, there are some other errors that you can make that are confined to a single MPI process. But then if you program an MPI application, you don't have a single MPI process. Most of the time you have multiple different processes, and then you can make even more errors that may be harder to catch for correctness checking tools because they involve multiple processes. An example would be wrong call ordering of collective operations. So if one rank first calls an MPI barrier and then an all reduce, and the other rank first calls the all reduce and then the MPI barrier, you end up in a deadlock situation, which is also not desirable. So we see that there are several different categories of MPI errors. And the MPI-BugBench is designed as a test suite to test these correctness checking tools. And we have a unit test-like design, meaning that for each error, we have one test case that tests for the given error. The test cases are then generated with some Python scripts, which basically look like this. So what we do here is we generate the test cases. So we go through all the different functions that MPI send offers, like send, ISEND, RSEND, BSEND, and all the other functions. And then we want to introduce an error, basically. So we cycle through different invalid values because giving the send function a null pointer will lead to an error, but also giving some other MPI constants like MPI in place for MPI send operation. It's also an erroneous argument. Then we basically get us a default template which gives us a correct MPI test case, just a default send-receive template where one rank sends and the other one receives. And then we want to introduce an error into the now correct template. So what we do is we need to search for the MPI call where we want to introduce the error. In this case, we want to introduce the error on the sending side, and the default template is structured in the way that always the rank 1 sends and rank 0 receives. So then we search for the correct MPI call where we introduce an error, and then we are going to introduce the error, in this case by setting the buffer argument here to the invalid argument there. And then we mark that this call has an error so that the test harness can then see the tool that an error is expected and then check if the correctness checking tool reports an error for this given program. And then we can also set an appropriate error description to be used as the file name for the test case. And we see here is we don't only check for one invalid value here, but we check for multiple different invalid values here. Because what we want to do is we want to check for different instances of the same error. So first we incorporated all the different error classes so that we cover all the different kinds of errors that you can make in MPI. But then we also expanded upon this so that we now can also check for different instances of the same error. An example why this may be important is here. So if you have this send and receive operation, you see it's a data type mismatch. And in this case, the data type mismatch will lead to a different size of the message. But here we also have a data type mismatch. And here maybe for the correctness checking tool, this kind of mismatch is a bit harder to detect because it likely will not result in a different message length. So the question for the real-world applicability of the correctness checking tools is, can we find the error not only in one instance, but can we find the error in different instances? Basically, we want to test different usage patterns of MPI if the correctness checking tool can understand the different usage patterns of MPI and can detect these kind of errors in different usage patterns of MPI. So we don't want to go in here and say, okay, we have this type of mismatch, and then we tick the checkbox. The tool can find data type mismatch, but we want to go a bit more deeper and find out, okay, what kind of data type mismatches can be found by the tool. Maybe some kind of data types cannot be understood by the tool, and then those kind of mismatches cannot be found. Of course, with this kind of test case generation approach, there is a problem here. It can lead to a very high number of test cases. Since we have an automatic generation of test cases in MPI-BugBench, you can generate all the erroneous combinations of MPI predefined data types, and then you will end up with 4 million test cases where you probably test way too much. So therefore, we came up with different test case generation levels in order to strike a balance between testing multiple different cases of the of any given error. So having a very thorough correctness benchmark that very thoroughly tests the tool. And on the other hand, we also want to have a very efficient evaluation, that we get quick feedback on the tool, that we don't have to execute 4 million test cases. So we have different levels here. So the level 1 basically means basic cases, and this means that we find one example for any given error. We only include one example. So for the data type mismatch, we will include one data type mismatch there. Then we have level 2, which means sufficient coverage of usage patterns. So sufficient coverage of usage patterns means if we have think about the data type cases again, what we want to test the tool is we want to test if the tool can understand all the different data types that there are defined in the MPI standard. In order for that, we don't need to check every possible combination, but we need to check the combinations in the way that the tool is presented with each data type at least once. So we picked the erroneous combination so that the tool sees each data type at least once. And the same goes for other invalid values. So we try that the tool sees each invalid value or invalid usage pattern at least once. And then we can also have the full coverage basically by having all the different erroneous combinations that there are possible. Then we also want to, we have level 2 and level 3 are defined into subcategories. So there is a sufficient coverage of real world patterns and sufficient coverage of all patterns. And the way this basically works is we can have a look at what are the usage patterns of MPI that we find in the real world. And then we only generate erroneous combinations of those kind of usage patterns and not of all kind of possible usage patterns that the MPI standard theoretically allows, because we want to check for the real world applicability of the given correctness checking tools. So how does this work? Basically, we want to score the real-world applicability of the correctness benchmarks. So we define the MPI usage pattern as the MPI call, including the relevant parameters like which data type is used in order to test if the tool can understand the data type, which reduction operation is used, the number of elements, if a matching wildcard is used, and for collective operation, maybe also the rank is important because the operation may be implemented differently if it reduces to rank 0 or any other rank. And then we can look at the dataset of real-world MPI usage pattern. The dataset we used for this is the dataset that I've presented last year at EuroMPI in Bristol. If you have any question on that dataset, please also feel free to ask question about this. We basically weight each usage patterns by the frequency of the usage pattern that we find in the real world. And this means that like reduction operation and other collective operations are very frequently used in MPI. So those count more towards the score. And then we basically have a score for each usage pattern, and then we go through the correctness benchmark and we ask the question, okay, is this usage pattern that we find in the real world, is this also covered in the correctness benchmark? And we can basically sum up the score. And in the end, we end up with a percentage score. So the percentage of the usage pattern that we find in the real world that are covered by the correctness benchmark. And this percentage is, as you see here in the figure, weighted according to the different MPI usages. So how frequently is these kind of usage patterns used in the real world? The interesting thing here is that you can use our real world data set. We are doing a general study here, so we use a general real world data set. But you can also use a data set on the usage patterns that are used inside of your particular MPI implementation, and then you will generate test cases in order to test the correctness checking tools for the usage patterns that are specific to your specific application. And then it's very quick to decide which correctness checking tools or how well the correctness checking tools are suited to your specific set of use cases in your specific application. You just need to replace the general data set of real world usage with a more specific data set on your specific correctness checking on your specific application. So then we can visualize the real world applicability of the different correctness benchmarks. So we have COBE, the original MPI core bench, MBI, the original MPI bug initiative, and then our new MPI bug bench in generation level 1, which is basically just the combination of COBE, MBI, and RMA race bench included. And then we have this real-world guided generation of test cases where we generate the combinations in a way that we see at least each erroneous usage pattern, each MPI usage pattern at least once in an erroneous way. And then we see that we were able to greatly improve the real-world applicability according to the scoring mechanism I explained on the slide earlier. We are now able to cover 75% of all the usage patterns of MPI that we find in the real world. As you see here, there are some white spaces still missing. They mostly resolve about MPI-IO because MPI-IO is not covered by the benchmark so far. And also currently we only focus on the benchmark is written in, the benchmark generates codes in C. So we only include C, C++ usage pattern here, which explains the additional white spaces here because the Fortran usage patterns are not considered so far. Nevertheless, the most important or many of the important usage patterns, 75% of all the usage patterns that we find in the real world are now also part of the benchmark suite. So then we can test the correctness checking tools with our new benchmark suite in order to check for the real world applicability. So we check the 3 most relevant state-of-the-art tools. One of them is ParCoach. Semi has already mentioned the tool. We check ParCoach for the original version, not with the stuff that Semi's improvements there. We did not include that. ParCoach is a static analysis tool, or we only use the static analysis part of that. ParCoach was also extended to include some dynamic data race detection. We did not use that, so we only use the static part. Static means that it compiles the test cases and then analyzes the test cases during compilation time. There are also 2 main dynamic tools around. One of this is ITAC that checks for different kind of errors, such as general tool, and also must is a general tool that basically intercepts the MPI call at runtime and then perform correctness checking at runtime. So we can have a look at the results here. Basically, we are performing a minor reclassification task. This means that it can result in a true positive. So there is an error in the test case, and also the tool reports an error. Yeah, note that I said the tools report an error currently. In this evaluation here, it's not checked if the correct error is reported, because sometimes it may be questionable what the correct error actually is. So we have the case where the tool detects an error, and there is an error in the source code, so a true positive. We can also have a true negative, where the tool doesn't report an error, and there is actually no error in the test case. So we also, of course, include correct test cases to check for false positives. Yeah, false positives. The next category means that the tool detects an error, but there is actually no error in the test case. And then you can also have a false negative, where the tool does not report any error, although we know that there is an error in the test case. We also encounter some runtime errors. If you pay very close attention, there are some runtime errors for must. I will explain them in a minute. Runtime error means that the correctness checking tool basically crashed. It leads to some runtime error inside of the correctness checking tool. Therefore, we only check for runtime errors on correct MPI test cases, because for erroneous MPI test case, we don't know if the runtime error, for example, the MPI library crashing, is a result of the correctness checking tool doing something wrong, or is a result of the actual error that is present inside of the test case. And therefore, we only check runtime errors for correct test cases, but for a correct MPI code, the correctness checking tool should not lead to a runtime error. We also found some compiler errors, and these are basically the result of the Intel MPI version that we used for ITech not supporting all the MPI 4.0 features yet, and then compilation fails for those test cases. As you see, with true positive, true negative, false positive, we can also derive the standard metric like precision, recall, F1 score. You find those metrics in the paper. I will stick to the visual representation of those for the presentation. So overall, we see that actually there's a lot of green here. If we have a look at just the point-to-point operations, we first see that ParCode is not designed for point-to-point operation. It's designed for collective operations, so we don't expect it to find any errors for point-to-point communication. And we here again see the problem with ITech and that it does not support all the MPI 4.0 features yet. But we also see that actually many of the errors are already covered, and the tool can find many errors. For collective operation, this actually looks a bit better here. ParCode now is able to detect much more errors because it is designed for these kind of collective operations. In this case, some errors may not be detectable at compile time statically, or it may be very hard to detect those kind of errors, but static analysis tool obviously has the advantage that it do not need to execute the test case, so you maybe get feedback a bit faster. We see that in general, many errors can be found for collective operations, which is especially important because collective operations are the most common operations that you find in MPI. And if you pay very close attention here, we see that there are some runtime errors for must with collective operations. And those runtime errors only occur with certain data type. An example would be MPI double int and such data types that you can use for the minlog maxlog reduction operation. And if you use such a data type, then must basically crashes because the tool didn't understand the data type properly. And therefore, it is really important to test for the real-world applicability of the tool. Not only test with one data type if the tool can find data type mismatches, for example, but also test with several different data types. Because if you use a certain data type, in this case, the relatively special data type that are basically only needed for the minlogs maxlog reduction operation. If you test with those kind of data type, the implementation of the tool is general, as we see here. In general, it is capable of finding many errors, including data type mismatches. But for those kind of special cases, the tool fails currently. And I hope it will be fixed in the future here. So we see that it adds some value by testing lots of different kind of like the same error, but in different MPI usage pattern in different circumstances. Overall, we see that the tools generally, the most important use cases are covered by the tools. Unfortunately, the picture looks a bit worse for one-sided MPI operation. So one-sided MPI operation can be considered, especially complex. And here the tool support currently is quite limited in the way that many errors are currently missed by the correctness checking tools. So we see that there is potential improvement for the future here to get more support for these kind of one-sided MPI operations so that the users get more help in using this one-sided operations correctly. Overall, we would say that actually the tools perform quite reasonable, considering that MPI is complex and that checking and performing programming correctly for these kind of distributed application can be quite complex, and especially we consider that the tools actually cover the most important aspects of MPI. Yeah, the error cases that they currently do not found are very niche or are basically the result of using one-sided MPI operations. We unified the MPI correctness benchmarks into one unified benchmark suite, MPI-BugBench, and therefore the MPI-BugBench can check for the real-world applicability of the correctness checking tools by testing for multiple instances of kind of like the same error in order to point out some implementation defect of the tool. Yeah, we say that in general, the tools are, for example, with the must example, are able to detect data type mismatches, for example, but in some specific situation, the current implementation of the tool falls short to really cover everything that the MPI standard offers. But in general, the overall tool support is quite reasonable. And with this, I want to thank you for your attention, and I'm looking forward to have an interesting discussion.
Questions?
Yeah, thank you for the talk. I'm wondering what's the number of different patterns are in your test suite, because when for my work I looked at all the different correctness benchmark suites, and the problem I saw is that, for example, MPI is like advertising 900 test cases, but they're essentially just 10 patterns, which does the other like codes like combined with each other. And I think the problem I saw with the different correctness test suites are that they all had like dynamic tools in mind, because dynamic tools, it's not that important to have different patterns, but for static tools, it could be like a huge difference in terms of how good they can detect errors.
So what we here define as a pattern is a usage pattern in MPI. So the MPI call, of course, and all the parameters that go into the MPI call. We did not check for different usage patterns in terms of like try to challenge the static tool, like for example, put something into an if branch that is only available at runtime in order to try to challenge the static correctness checking tools more. So we did not have a look into that yet. And I cannot, out of the top of my head, directly answer the question about the number of usage patterns that we considered. I have to look that up.
And because I was like always thinking about like suggesting like another level of category, which is like the degree of like statically available of necessary information, something like that, because like it's a huge difference. Like if you know which communicator is used, do you know which ranks are operating something, and so on. Like you can do like lots of stuff. And then, for example, for the PyTorch results would be like probably decrease a lot if you also have such test cases, for example.
We also thought about that, how to incorporate that. It has more aspects than just the amount of statically available information, because you can also use that in order to showcase an advantage of static tools, that if there is an error in a source code branch that is not going to be executed at runtime, like the other way around, basically, then you can use that in order to showcase an advantage of static tools and test if they can find the error in the other given branch here. So I guess this is something that we want to look into in the future as well.
And for example, in the paper from CoreBench, they had like different levels of test case. Like for example, like micro benchmark test case, like 20 lines of code basically. Then they said, okay, we also plan to have test cases which are multiple modules and so on. How about like this BugBench? Is it also planned or?
So in BugBench, it is also planned to like incorporate that. The current work only incorporates like the basic level of CoreBench, basically, where we have one single file per test case. But again, of course, especially for static tools, it would be nice to have, like, for example, multiple objects file, different translation units to test if the static tools can also handle errors across different translation units.
Yeah, thank you. And last question, maybe. You show that like you have like 4 million of test cases, but in the results you show like thousands. So
Yeah, so we I maybe should have pointed that out. So we always use level 2.1, and we suggest that you use level 2.1 as the default level, basically, because we think it's very suitable point for the trade-off between having thorough correctness checking, like testing for all the 4 million test cases, and running less tests to get a more efficient evaluation. And we think that this kind of sufficient coverage, where we see each usage pattern at least once in an erroneous way, is the good trade-off point here. So we always choose level 2.1 here.
thank you. One question, sorry. What's about different program models? Because like, for example, RaceBench, it has like 3, like MPI, SHMEM, and GASPI, for example. And for example, I would like to see that NICO, ND, SHMEM, and so on. Have you thought about that?
Yeah, so currently the MPI-BugBench only consists of pure MPI programs. For example, for MPI core bench, there is also an add-on testing MPI plus OpenMP errors. And of course, we want to include such programming and also maybe other access in the MPI plus X model in order to test for different errors, because it turns out that if you combine MPI plus OpenMP, then there is not only MPI errors that you can make and only OpenMP errors that you can make, but the combination of both results to the possibility of making more errors, where correctness checking tools actually need to figure out more than just the OpenMP and just the MPI side of things.
Thank you.
Thank you. One more question here.
Yeah, I have actually 2 questions. Maybe it's so. The first is related how do you actually describe the patterns and generate from them all these million of test cases then?
So the patterns are basically described as a table where the MPI call is listed and all the parameters that go into the MPI call. And then how the different levels are generated is, if we have a look here, is basically we go through all the different values there, and then we check if the values that we use are in this table that describes all the data sets, the large MPI data set that we have.
Okay, thanks. And the second question is about the one-sided communication. So what makes it hard and to have some thorough testing there? Do you need some additional help from the compiler here, maybe? Just not from the benchmarking side, but from the implementation of the tool side. Maybe you can share some.
Yeah, I'm not. I've not written the tools myself so far. I can only share a general idea that I have. I think one problem is that there is something that interacts with your memory that comes from like the different process, and then the question is, and also some questions are, especially with these sort of like data race situation. Especially for dynamic tools, is the non-determinism that is involved there. Because a data race does not mean that it always leads to a program crash, an observable error in that sense. Yeah, because maybe the ordering of operation was right by chance and not by means of proper synchronization, which means that you have an error there. But the challenges of non-determinism comes in that actually you don't see the error at runtime. And then the question is it even fair to assume that the correctness checking tool should pick up that error? It also happens with OpenMP if you combine MPI plus OpenMP. And as we perform that evaluation, we see that we basically try different orderings of the different interleavings of the thread. And sometimes the correctness checking tool itself has an impact on the interleaving of the thread in the way that the error actually goes away all the time. The tool is not able, because of the runtime influence of the tool, the error does not occur anymore. And then it's very hard to do the correctness checking point here. So we also want to have a look into it. How can we handle this non-deterministic stuff? How can we check if there was, for example, interleaving of the different processes, that the error was just very unlikely to occur at runtime? And then, of course, if you have the best tool available, then it would still point out that there is a data race, because the interleaving of the different processes in the case of RMA operation was correct just by chance. And I guess it's very hard to find that out.
Is there a question in the front here?
Well, I think you got answered, because I was going to ask something along the lines of, so your false positives and your false negatives, right? You've categorized them, but I mean, have you considered just a category where like we are uncertain whether there will be, but this could be prone to a data race? So right now you're trying to determine one, right? But you could just be like, this could be a region in terms of like, if I'm using this tool, I'd be like, oh, I should look back at this code.
Yeah,
because it might be prone to this type of data race issue. Whether it's an error or not, you don't let the tool determine. You let the tool just say, this is a region of interest. Have you considered that as a possibility for the tool?
For the current evaluation, what we did is we only check if there is an error reported.
Yeah.
But what maybe also is important to check, for example, for the helpfulness of the error messages.
Yeah.
So you can sometimes must, for example, distinguishes between an error message and a warning.
Yeah.
We also said that the warning is also treated the same as an error message in terms of our evaluation. So if we get a warning, then we also treat it as, okay, it found the problem in the source code. But the question is also, what is the problem in the source code to begin with? For iTech, it's better. So there are, do I have some time?
Oh, I think we're at the end of the.
Okay, then I can share this in the lunch break.
We can take this offline.
Yeah.
Thank you.